Welcome. This video shows how to use Molecular Knowledge Systems' web application for finding binary azeotropes. You can find the web application by navigating to Molecular Knowledge Systems' homepage, clicking on the Library tab, scrolling to the bottom of the page, and then clicking on the Azeotropes case study. The web applications page provides details about the methodology used to predict the occurrence of an azeotrope in a binary mixture. It provides background on the methodology, a derivation of the equations used, an example use of these equations, and evaluations of several binary mixtures. In summary, here we show a graph depicting the vapor-liquid equilibrium curve for the binary mixture of acrylonitrile and cyclohexane. The y-axis denotes the mole fraction of acrylonitrile in the vapor phase, and the x-axis denotes the mole fraction of acrylonitrile in the liquid phase. The vapor-liquid equilibrium compositions are shown by the black curve. We see that this equilibrium curve crosses the 45-degree diagonal line. At this crossing point, the composition of acrylonitrile in the liquid phase equals the composition of acrylonitrile in the vapor phase. This is the azeotropic point for this mixture at this pressure. We also see that the slopes of the equilibrium curve at the limits of pure cyclohexane and pure acrylonitrile are both greater than 1. This means that the values on the equilibrium curve start and end on opposite sides of the 45-degree line, which has a slope of 1. Since the equilibrium curve is a continuous curve, if it has values at the starting limit on one side of the diagonal and values at the ending limit on the other side of the diagonal, then at some point it must cross the diagonal, meaning that at some point it will have an x value and y value that are equal, meaning that the mixture will form an azeotrope. We can calculate these limiting slopes in terms of basic physical properties, specifically the infinite dilution activity coefficient, the vapor pressure, and the boiling point, which is the temperature at which these properties are determined. The derivation of these equations, again, is given further down on the web page. You can use the web application to determine if a new chemical forms an azeotrope with a second common chemical. As the first step, enter the new chemical's molecular structure in the MKS structure editor. We will call this chemical component A. For example, we enter the molecular structure of cyclohexane. First, we enter cyclohexane's atoms, and then we bond these atoms together with single bonds. The second step is optional. We skip this for now and come back to this later. In the third step, select component B from the list of common chemicals. For this example, we select benzene. Then, in step 4, enter the pressure at which we want to determine if an azeotrope forms. We enter 101.3 kilopascals. Finally, press the Identify Azeotrope button. The information we entered will be sent to a WebServer edition of Cranium running in the cloud. Cranium will estimate each of the required physical properties for component A, retrieve or estimate the physical properties for component B, use these physical properties to determine the limiting slopes, and finally use these slopes to determine that cyclohexane and benzene do form an azeotrope at 101.3 kilopascals. Scrolling back up to our structure editor, we can repeat our example using methyl cyclohexane. We add a carbon, and bond that to the remaining structure. Again, we press the Identify Azeotrope button, and the information is sent to the WebServer edition of Cranium, which again estimates the required physical properties, from which we calculate the limiting slopes and determine if an azeotrope is formed. In this example, the app determined that methyl cyclohexane and benzene do not form an azeotrope at 101.3 kilopascals. As a final example, we again scroll up to the structure editor and add fluorines to our methyl group. We add 3 fluorine atoms and bond those with single bonds to our methyl group. Again, we press the Identify Azeotrope button, and again the properties and limiting slopes are calculated. In this case, the web application determined that trifluoromethyl cyclohexane and benzene do form an azeotrope at 101.3 kilopascals. It is important to note that the determination of an azeotrope can be quite sensitive to the values of the required physical properties. In particular, it's important to have a good estimate for component A's boiling point. For example, Cranium estimated the boiling point of trifluoromethyl cyclohexane to be 262.93 Kelvin. If we know an experimental value for the boiling point, a value that's different than our estimated value, we can enter that boiling point in our optional step 2, the step we previously skipped. If we enter, for example, 380 K, and again press the Identify Azeotrope button, we see that Cranium now uses this entered boiling point value to calculate the required vapor pressure, activity coefficients, and limiting slopes. The value of these slopes now indicate that an azeotrope is not present. We hope you find our Azeotrope-Finding web application useful. We would greatly appreciate any feedback you can give us, especially on mixtures that you find are correctly or incorrectly predicted. This will help guide our continuing search for new estimation techniques that can improve the accuracy of Cranium's physical property estimations, and thus this web application's azeotrope predictions. Thank you.